Hello. Today I'm going to be going over the test that we had today and just giving like a answer guide. Basically, I'm not going to use the exact values because I don't remember them. Um, and I might not even input numbers depending on how simple the problem is. Yeah, but I'm going to be going over the general ideas surrounding every one of the problems. So the first problem was set up like this with a hydraulic system basically with two plates. And so this was all full of water, blah blah blah. And so basically they had a mass, call it M1 on this plate and oops, M2 on that plate. And so basically we were asked oh, and we were given the radius of one of the plates. And we're assuming that the plates are like circles. So it's like that and like that. Right? And we're given the radius of one of the plates, right? All bit do big R. And it's asking us to find the radius of the other side, which is little r. So if we look at this problem, this is I believe it's called Pascal's principle, something like that problem, where basically we have to assume that the pressure is the same throughout the entire system. So basically, the pressure that this mass 1 exerts is going to be equivalent to the pressure that mass 2 exerts. And we know that pressure is mass over area, mass being kilograms usually, and area being meters squared. And so basically, from this, we can determine M1 and M2. Sorry, I take that back. It's not the mass, it's the force. Sorry about that. Force over area. Okay, that makes more sense. And we have newtons, not kilograms, and meters squared. Yeah. And so basically, for this, we're going to now take the force of mass 1 exerts on there versus the area of mass 1. Set that equivalent to force mass 2 exerts and the area of mass 2. So if we look at the forces that each mass exerts, we can draw a free body diagram. This will be our plus direction, positive. So mass 1 has a force downwards of m1g. Of course, it has a normal force. And it's not moving, so there's no acceleration. And mass 2 has a force, of course, a normal force, and a downwards force that we're paying attention to of m2g. So now all we need to know is how do the areas relate. So we can basically plug in these two values into our equation, which is this, and we get m1g over area of 1. The area of, how about this one, is going to be pi r squared. So over pi r squared, and that's equal to m2g over pi big R squared. And then if we're just solving for, let's say, big R or little r, we could just cross multiply and then find r, I'll do little r, as equal to the square root of pi times a bunch of stuff. That's going to be um, m1g times pi r squared, right? Because we cross multiply these. Then we're going to be, oh, sorry, the pi is not here. Let me erase that. Pi will not end up here. And then this is just going to be divided by pi m2g. So pi m to g, and we notice we can cancel some things out. G, and we get m1, m2, r. So basically, r equals m1 r squared, I guess, yeah, over m2 all square rooted. So that was the first problem, part one. 1b was discussing now basically what would happen if we push down on our contraption here. We push down on one side with a distance of x. How far up will this side go? And so we're given, again, like a radius or something of both of them. And then we're also given like some masses, but that doesn't really matter that much. I'm going to label the second radius actually as little r just to make that clear. So the reason why the masses don't really matter is because we know in Pascal's principle that basically the force times distance is for this is just work basically, but force one times distance one equals force two times distance two, and it's even simpler than that, basically, because what we're saying is that if this is equally compressed, the amount of area or volume displaced here will get replaced up here. So if we're pushing down with x, the total volume on this side that's displaced will be, so that's r pi r squared times x, so x pi r squared. That's equal to pi r little r. Let's say the distance up is y, pi r squared y. So then to solve for this distance up, all we really have to do is say y equals x pi r squared. That's supposed to be a 2, a little bit clearer, over pi r squared. Pi's cancel, we get y equals x r squared over little r squared. And that's just the distance that gets pushed up. That's basically it for the second part of the first problem. So now moving on to problem two. This was focusing on impulse. And so basically, it was saying that we had a cube, some mass, and it was accelerating, or I guess it was accelerated by a force over a distance, let's say, or no, it was a time period over a time period. So it was accelerated into a elastic wall, right? And it wants us to evaluate the basically the impulse or change in momentum that the wall caused on this box. So first of all, we need to define positive direction. So I'll do there and there. And next, what we have to do is we have to find what V initial is, so right before the collision, and then V final. And because this is perfectly elastic, we actually know that V initial equals negative V final, because it'll be bouncing back with the exact same speed as it came, except in the opposite direction. So to solve this, we will use a momentum sort of trick. So to find the momentum of the object, it's mass 1v1. Sorry, not a momentum trick, a impulse trick. So to find the change in momentum, we know that change in momentum is also equivalent to force over a period of time. So initially the box is not moving at all. So basically its initial momentum is going to basically be 0, right? And then its final momentum is basically going to be equivalent to F delta T. And we also know that change in P is equal to P final minus P initial. P initial is 0 because it's not moving at all. P is momentum, by the way. Then that means P final is just going to be equivalent to F delta T. And P final is the um, final, what's it called? Momentum that this mass is like basically accelerated to, right? So it'll be the amount of momentum it has right before the collision. So I'll be like PF right here. But again, it's a little bit confusing because this is before the collision, and yeah. So yeah, okay. And also just to be clear, volume or not volume, velocity is proportional to momentum. So this also means that P initial is equal to negative P final. This is the first P final, so I'll do PF1. This is the actual P final. So to find this, all we have to do then is basically say um just say F delta T, and we are given F and T. And the change in time is just going to be the time it's specified, unless it's like 20 seconds to 30 seconds. You kind of get the point. Also, I realize that labeling this as P final one is kind of confusing. I'll just label it as P initial, but this is not the same P initial as this one. It's basically this one. And this is kind of really confusing, but basically all we need to know is that the box starts with P initial of F delta T, and then it ends with a P final of basically negative F delta T. So the overall change in P by the wall, if this is positive, is going to be P final, which is going to be negative F change in T, minus P initial, which is going to be F delta T. So the total change in momentum is going to be negative 2 F delta T. And so, yeah, so that makes sense if this is our positive direction, because basically the box is pushing it enough to stop it and then pushing it enough to send it back exactly at the same speed it was, except in the opposite direction. So it's negative 2 F delta T. So, I'm trying to think what the second part of this problem was. 2B. Hmm, interesting. I don't remember. It probably had to do with impulse. Right, basketball. So it was basically talking about a basketball with a height dropped from a height. Let's call it height one, height initial, whatever. And then it bounces back up with a height final. And so it wants us to say how much impulse is exerted by the floor in this situation, right? So if we're dropped from a height of one, we basically want to find what the velocity of the ball is here, right? And also we're given a mass of the ball. It's not going to change. So we want to find the velocity at this point and then right after the collision. So how we can do that is simple kinematics. So we can use the equation no, we have to do another one. I think there's a combination equation, but I'll just do x equals 1/2 at squared. This is assuming we start with no position and no initial velocity, which is what it's saying. It's saying it's basically just starting and then it's being dropped. And so basically, the x distance it travels, I'll do this as positive. This direction doesn't really matter. I'll do that positive. So basically, the x is the final position, so that'll be negative h1 equals 1/2 of acceleration, accelerated by gravity. So that'd be 4.9 t squared. Of course, gravity's going downwards, so that'd be a negative acceleration. These cancel, and then to solve for this time, which you'll see why we need in a second, we just get the square root of h1 over 4.9. So this is height 1, and this gives us the time it takes for it to go from here all the way to the ground. And that'll help us calculate the final velocity, because now we know the acceleration. So now we can use v equals VO plus AT. Of course, there's no initial velocity, so I'll just say v equals acceleration times time. And we know what our acceleration is. and we know what our time is. So basically, the velocity initial before impacting is going to be 9.8 times the square root of h1 over 4.9. Okay, so now that we've solved this, we now need to find the final velocity that this object has. So the final velocity is going to be a little bit different because it's going to be going in the opposite direction. But we can use the exact same method by basically plugging in 1/2 at squared into this with hf instead. And basically we'll find out that v final is going to basically be the exact same. So what we're doing though is we're calculating as if it was dropped from here because we know if it's dropped from here versus if it bounces up perfectly elastically, it'll have the same velocity, just different directions at this point. So all we have to do then is just rewrite this, but instead of h initial, we have h final, and we have to make sure we're accounting for direction. Of course, for velocity initial, I forgot to add a negative, but given our axes, the positive direction is up, and this is traveling down, and this one is traveling up. So this will be a positive 9.8 times h final this time over 4.9. So now all we need to do is basically find out what the impulse is. And impulse, we know, is P final minus P initial. And we're given the mass, we're given velocities, so all we have to do now is plug them in. So change in P is equal to mass times negative 9.8 root h1 over 4.9, and then minus um, m times positive 9.8 root h final or 4.9. So we can also simplify this a little bit further by saying change in p by factoring out m equals m times negative 9.8 h1 over 4.9, and that's a square root, and then minus again 9.8 root h final over 4.9. So this is basically our final answer. You have to plug in a few numbers to find the total impulse, but other than that, it's pretty simple. So let's move on to 3A. So 3A was asking what would happen if a ball launched at a initial velocity with a angle of given hits and with a given mass goes up, and at the top of its arc it hits another mass of a known mass. So I'll call it mass 1, mass 2. This is attached to a rope. How high up will this swing at its maximum height? Might seem a little overwhelming, but if we remember how two-dimensional, I think it's called dynamics, kinematics work, basically we know that the velocity in the x direction is always the same. So in this case, it's going to be VO cosine theta as our velocity right before the impact, right? And of course, M2 is not moving at all before the impact. So we can basically just use momentum equation M1 V1 equals no, a final velocity. And by the way, inelastic, forgot to mention that. So they stick together. V final M1 plus M2, right? We're just going to solve for this final velocity here. And we know M1 V1. V1 is just going to be that. And we know our masses. So we can plug it in and solve for VF. So V final equals M1 V naught cosine theta over M1 plus M2. So now that we have this, basically, you want to figure out how high it goes, right? This is m2 plus m1. So they're going to be stuck together and they're going to be traveling a distance. And we want to figure out what this height is. So basically, what we're going to be doing now is we're going to be using energy. So 1 half mv squared equals mgh. So right away, cancel out the masses, not worry about that. Right? We know what our v is. It's v final, which we have right here, and we're just solving for h. So basically, all we have to do is say h equals all this stuff, m1 v initial cosine theta over m1 plus m2. This is going to be squared and then divided by 2 and g. And that's it for this problem. That'll give us the height it travels in this direction. For 3b now, we have the same situation, a ball launch, blah, blah, blah. Hits here. But this time, we want to figure out how far it travels in the x direction, right? And the equation is now elastic. So we're again given an angle, velocity initial stays the same, but now we're going to have to account for the discrepancies because it's an elastic equation. So we're going to set up our two equations, m1 v1. I'll just do that, m1 v1 prime plus m2 v2 prime. And then the other equation we're going to use is v1 plus v1 prime equals basically v2 prime. There would be a plus v2 initial, but there's no initial velocity for mass 2, assuming this is 2 and this is 1. And so basically, now all we have to do is plug in. We want to figure out what the velocity of v2 is. So now we just have to get rid of v1. So I'm going to solve for v1 in this equation, sub it in there. We'll get m1 v1 equals m1 times v2 prime minus v1 plus m2 v2 prime. And so now to simplify this, basically I'm going to just factor this out and I'm going to shove all the terms that aren't v1 or v2 prime, sorry, onto the other side, which is going to be negative m1 v1, which will turn into 2m1 v1 on this side. And then we'll still have v2 prime times m2 plus m1. So we have these two, m1. And so basically, we are now going to get an equation for v2 prime of 2m1 v1 over m1 plus m2. Now, with this equation, we're going to be doing roughly the same thing as the last one. So we can recycle our uh, energy equation, 1 half mv squared equals mgh, solving for, I guess, the height. So we can get height equals v squared over 2g. I believe so, after masses cancel out. So what we have to do here now is figure out how far it travels in the other direction. Because we're also given, I forgot to mention, the length of the string. So if we think about it, the height it travels will create a triangle, right? So the hypotenuse is still L, and this is the height it travels up. Height, and we're looking for X. So all we have to do now is basically either use some sort of sine, cosine, or we can just be lazy and say L minus H is this side. So then we can use the Pythagorean theorem. So we get L minus H squared plus X squared equals L squared. And so to solve for X, we just get X equals the square root. Ooh, I'm going to have to draw this on another page. Um, yeah. So x equals the square root of I'll do squared, L squared, and then we're going to be subtracting L minus H minus L minus, and I'm gonna leave a little bit of room to write in our H here because I've kind of been not keeping up with all our terms. So I'm gonna slow down a little bit, and I'm gonna do L minus, this is our whole H term, which is going to be very confusing. So we're starting with V squared, which is going to actually be V2 prime squared, which is a final velocity, which is this. And V1 is actually going to be VO cosine of theta. So I'm going to write this all out. It's 2 M1 M1 V naught cosine theta over M1 plus M2. 2. All of this is going to be squared and divided by 2g, all within the brackets. And that is our final answer. I believe so. I might have made a mistake somewhere, but this is roughly what you're going to be end up doing. And it's a little bit annoying. I feel like a little bit tedious, but plugging all this in shouldn't be too hard. So, yeah. So that brings us to problem 4. A. So problem 4A is a trick question. So basically it has a object, call it a vessel, and I'll just draw it like this so it makes more sense. This has a mass of mass 1, and they have a object with a mass of mass 2. And so this is floating along in some water, and they give you the length. We're assuming they're perfect squares. They give you length here, and then I'll make this little L. Right? They give you length here, and then they ask what percent is submerged in water. And we're also given that the density of water equals 1,000 kilogram per meter to the power of 3. So it's asking you basically what percentage of this is submerged. So you might be freaking out and being like, what do I do with all this stuff? There's so much air here. Do I have to calculate that? We're going to assume that air is negligible in this case. And we're going to instead look at Archimedes' principle. I think that was the dude's name. I don't know. But basically, we're going to say that pressure is equal to mass over volume. Not pressure, density. Sorry, it's a little bit confusing that we use P for density, pressure, and momentum and impulse, but it's fine. So, anyways, we have mass over volume. And so basically, when we compare the density of an object versus the density of water, assuming that the object is floating, it'll tell us how much this object is submerged. So if we assume it's floating, we could also calculate that, but we're going to be pretty sure that it's floating. We'll see later if the density ends up being bigger if you actually plug in real numbers. But basically, this will give us the percentage floating, basically, the percentage out of water. So all we have to do now, since we're given density of water, calculate the density of our object. So we have our mass, which is going to be m1 plus m2. And then that's going to be divided by volume, which is just big L3. We don't have to worry about little l. They give you that. That's just a trick question. You don't have to worry about that. Right. And so then this basically is our density of the object. And we're going to just divide that by 1,000 to get a percent floating. Right. So we'll get some number, right? Some percent. And to determine how much out of water that is, we're going to just multiply all this by L. And that'll give us how much it is out of water. Equals, I'll say distance x. Sorry, how much of it is underwater. You'll be able to tell because this will give you the ratio of how much is underwater. And then you can calculate how much is over water by also subtracting it, but you don't have to do that. And so for the final problem, 4b, It showed like a crane with a string attached to it holding a ball underwater. And so this ball was given a mass and a radius. So radius. And then they're asking, what is the tension in the string here? So we have to start by, of course, defining axes. Hopefully I did that on problems where it mattered. This will be plus. This will be plus plus. Okay, anyways. So we're given this, and I'll just say this is upwards. So let's draw a free body diagram of this. So it has a mass of m. So gravity is, of course, pulling it down with mg, but something's pulling it up, tension. But one other force is, which is the force of buoyancy. So to calculate the tension, we're going to just basically calculate the force of buoyancy and subtract that from mg. So tension equals Fb, negative Fb, plus mg. So you might be like, how do we calculate force of buoyancy? Well, force of buoyancy is basically the volume of water displaced, so the volume of this object, times density of water. And mg is just the mass times gravity. Oh, sorry, I forgot to multiply this by gravity. Right? So now all we have to do is figure out the volume of our object, which is going to be the same as the volume of water displaced because it's fully submerged. So force of buoyancy equals volume of a sphere is 4 over 3 pi r3, I believe. And this is our r. And then times density of water, we already said was 1,000. And then basically we're going to subtract that from mg. So the total tension is equal to mg minus 4,000. Oh, this is also multiplied by g. 4,000 over 3 pi r 3, and then I'll just slap a g on there too. So that's basically it. That's the last problem. This is just a simple walkthrough on the physics behind the problems, not an actual answer key. But let me know if I did any of them wrong. I might have made some mistakes. I think I corrected most of mine. But yeah, please let me know. And thank you if you made it this far, actually. So yeah.